In this unit, we're going to study the main definition of a collector, the main features, and the main components that are going to affect the behavior of this component which is located in the solar field. First, we must understand what is a collector. In order to increase the optical performance, each module has a tracking system which is going to help this one to follow the sun throughout the day, because we are finding that both vectors, the normal vector of the surface of the parabolic trough and the vector of the solar ray must match, because the corrected DNI is going to be the same that DNI, because the corrected DNI is equal to DNI, direct normal irradiance, multiplied by the cosine of alpha, when alpha is the incidence angle. If both vectors match, the incidence angle is going to be 0 and the cosine of 0 is going to be 1. However, why we haven't got a tracking system for each module? Because this is going to increase very much the cost in the solar thermal power plant, and we must understand that the solar field is the main system in this plant. So we must group some modules in a set of modules which is called a collector. A collector is a set of solar collecting assemblies, solar collecting elements, SCE, that is modules, more or less from 8 modules to 12 modules, which has a common tracking system. For example, in this image we can see a collector, a solar collector assembly, which is made up by 12 modules, 1, 2, 3, 4, 5, 6, and other 6. That is, this is made up by 2 sub-collectors. As we are going to study in the following lesson, if a loop is made up by 4 collectors, each collector is going to have 12 modules, and if the loop is made up by 8 collectors, each collector is going to have 8 modules. Now we must define which are the main parameters in a solar collector assembly. That is the focal length. The focal length is the distance from the center of the parabolic trough to the focal point. The focal point is the line along the solar collector assembly where is located the HCE, that is the observer tube, where the solar radiation is going to be transformed into thermal energy. The average distance to focus, we must understand that the parabolic trough is not a semicircle, it's an ellipse. So the distance between each point to the focal point is going to be different, because the focal length is going to be from the center here to the observer tube, which is here along this line. But this length, the different lengths are going to be different. HCE radio, which is the observer tube radio, the place where the solar radiation is going to be transformed into thermal energy. Aperture width, which is the straight line from one end to the other end. The receiver area, which is the area which is receiving the solar radiation. Length of a collector, this is the length of each module multiplied by the number of total modules. Number of elements per collector, that is auxiliary systems, wires, and other subsystems. Number of mirrors per collector, that is we are going to have a mirror for each module, so really is the number of modules. Number of absorber tubes, because we are not going to have just an absorber tube, it would be very expensive. We are going to have some sections of absorber tube. Optical efficiency, which is the ratio of the solar radiation which is efficiently reflected into the observer tube to the total absorber solar radiation by the reflecting mirror. And thermal efficiency, which is the ratio of the thermal energy which we are going to obtain in the observer tube divided by the total incident, the total solar radiation which is going to hit this observer tube. For example, here we can see an example, the power block, which is we will study this in the 8th unit. Is located at the center. Here is the cold heater, the cold pipe, and here is the hot heater. As we are going to study in the following lesson, a loop is called loop because the hot pipe and the cold pipe is more or less in the same place. So we are doing a loop in the solar field as a collector, an SCA, solar collector assembly, and a loop is made up by several collectors. And here we can see the different common values. For example, for a Eurotrav collector model, the focal length is more or less 1.71 meters. So the dimensions of a collector is really high. The collector length, almost 100 meters. The aperture width, which is 6 meters. So the collector, the height of a collector is going to be more or less 7 meters. And finally, the mirror reflectivity, which is going to depend on the material. Always, this is usually silver, and the reflectivity of the silver is 94%. From this point to the end of this unit, we can see the different hierarchy of the solar tracking system. First, we have solar tracking system, control system, and finally we have the actuators, which can be hydraulic, electro-hydraulic, and the most used engine with a rack gear. Although nowadays the most used is hydraulic system. Solar tracking is the mechanism that finds the best incidence angle, because as we saw in previous unit, we know that the best situation is in which the normal vector of our parabolic trough matches with the direction of our solar ray. The best situation is in which both match and the incidence angle is 0 and the cosine of 0 is 1. So the DNI, the direct normal irradiance, is going to be the same that direct normal irradiance with this corrected factor. Here we can see the same concept that we saw in previous unit, that we haven't got just a solar ray. We have got a lot of solar rays, and they are going to hit this surface in the parabolic trough, and they are going to be reflected into the observer tube. The main two solar tracking systems are east-west orientation and north-south orientation. In east-west tracking system, we have got the observer tube is oriented in north-south line, and the tracking system is oriented in the east-west orientation. And the other north-south tracking system, the observer tube is oriented in east-west orientation, and our parabolic trough is being moved in north-south orientation. However, we have got east-west orientation and north-south orientation, but which system must be used? It depends on our purposes. We can see here that the behavior on a clear day of June, the north-south orientation, the system is able to absorb more average power than east-west orientation. However, in December is the opposite. East-west orientation is able to absorb more average power. However, we know that summer and spring are able to support more energy than autumn and winter. So the system which is able to absorb more average power will be the final decision, and the system most used in a solar thermal power plant usually is east-west orientation. Here our final decision is west orientation, We can see the absorber tube, which is oriented in north-south orientation, which is the heat collecting element, that is HCE, the parabolic trough, and the sun, which rises from the east and it sets in the west. Now we must define the different orientation mechanisms. We know that the solar tracking system is the first. In the second way, below the tracking system, we have got the control tracking. This control tracking is going to follow the different orders of the solar tracking system, and this control tracking is going to order the different actuators, for example the transmission unit, to move this parabolic trough. Now we have the control tracking. Control tracking is a system that monitors the position of the collector in function of the position of the sun throughout the day. That is going to follow the orders of the solar tracking system, because this one is going to measure the sun position in function of the solar clock, different sensors, and is going to order some different actuator, for example hydraulic system or an electric engine. This position is measured with the help of an encoder. An encoder is a mechanism that we will see in following units, but it converts some data, for example temperature or pressure, into digital code, that is binary code, that is able to be read by ADC or DAC. And end of carrier, that is a security element, and the main two ways to adjust this position of the collector is measured by a solar sensor. Although nowadays the most used system, the most used way is mathematical algorithm. And finally, the position control is performed by the log, that is local control of each loop. This concept will be seen in following unit, solar field in a solar thermal power plant. Here we can see the solar sensor, which is able to measure this temperature position thanks to different angles, and the encoder, which is going to transform this data, temperature, pressure, and the position of the sun, into digital code. Now we must understand what is a transmission unit. A transmission unit is the mechanism which is able to move this parabolic trough in function of the orders of the control tracking system and the solar tracking system. The main system which are classified as a transmission unit are electric engine, hydraulic system, and electro-hydraulic system. However, we must understand that we are not going to have a transmission unit only for a module, because it would be much more expensive. So we must group some modules into a collector, and we are going to have a transmission unit for each collector. Usually each collector has from 8 to 12 modules, and it is going to be easier. Here we can see an engine reducer and a hydraulic system. The first transmission unit is the electric engine. This is a very easy mechanism, and the main advantages are this is easy to maintenance and its simplicity. However, it has some disadvantages. For example, the electric power required is bigger than the electric power required for a hydraulic system. The consumption peaks would be high because of the huge elements. Although we are going to group some modules into a collector, the number of collectors is bigger, and the electric power required is very high, and the small oscillation caused by wind were down in a very short time, so this system is not recommendable. The second system preferred for a solar thermal power plant is an electro-hydraulic system, which is based on an electric engine, hydraulic system, and a rack gear. The system, although it's easy to operate and the maintenance is very easy, causes a small deviation in the ends of the collector, so which means that the areas located in the ends of the collector are not perfectly orientated. So the incidence angle there, although in the center of our collector the incidence angle may be 0 or close to 0, in the ends of the collector the incidence angle is not going to be the same. And we know that in some cases, for example, if we don't want in this moment that the parabolic trough are absorbing some power, this parabolic trough must have a quick blur, and this quick blur requires some instantaneous power, and this instantaneous power is very high. So this system has this problem that the power required for a quick blur is very high. Here we can see the system, and here a rack gear. Now we reach the main transmission unit for a solar thermal power plant, which is a hydraulic system. Hydraulic system presents some advantages versus the other system, and these are: it is more economical, the power consumption is lower because the electric engine is going to requires much more power, and the power consumption peaks are lower. For example, in this quick blur, the power consumption peaks are higher in electric engine than in hydraulic system. And the last advantage is that it can be performed up more or less 30 micro movements if this system, the hydraulic system, has got an accumulator, so the work range is very high. Here we can see two simple examples. Here in a solar thermal power plant, and here the schematic of the hydraulic system. Here we can see that this system is in east-west orientation because it has got a north cylinder and a south cylinder. So the parabolic trough is going to move in this direction. In the hierarchy of the solar tracking system, control tracking system, and the actuators, we must divide these actuators into transmission unit and ball joints. Because the collector is moving but the main HTF pipe are fixed, it's necessary to join the collector and the tube, and this is got with ball joints and flexible hose pipes. Ball joints has the main advantage that it has 3 degrees of freedom. So we have a sphere, a ball joint, and it has the yaw rotation, pitch rotation, and roll rotation. So it is going to let rotation in 3 dimensions. However, they often have oil leaks, which is the main disadvantages. So they can't do the required movement all time, and they must be changed for a given period, for example, one year or 2 years. On the other hand, we have flexible hose pipes, which are a cheaper way than ball joints, although the performance is lower because the ball joints are going to have 3 degrees of freedom because they are going to have yaw rotation, pitch rotation, and roll rotation, that is 3-dimension rotation, and flexible hose pipes just in an axis, and their expected usable life is lower too. Here we can see some ball joints examples. Here is the parabolic trough, and this is the HTF pipe. And here are placed some ball joints in the main joints. And on the other hand, we have the flexible hose pipes. Here we can see that this mechanism is not going to have a 3-dimensional rotation, but is going to have just a 1 dimension, that is in an axis. So the final decision is going to depend of our money or of other decision. Although if we have got enough money, we are going to invest in ball joints. To keep on in this unit, we must review some concepts that were seen in Unit 1 Solar Geometry, and it is solar position. The best system to define some position is the polar coordinate system. The main plane is going to be the horizontal plane, and here we can see the zenith nadir line, and it is the north-south line and east-west line, which are going to define this horizontal plane. And now we must review the different angles. Zenith angle is one of the most important angles, and it is the angular distance formed by the vector Sol observer and the observer's vertical. That is, we are here is the sun, here is our vertical, and here is the vector which join our position to the sun. And this angle is positive from here to the horizontal plane. On the other hand, we have elevation angle or solar height, and this is the angular distance formed by the vector sun observer and the horizontal between the observer and the vertical projection. So this is the complement of the zenith angle. Here we can see that we are here, and here is the projection of the sun. Here is the vector which joins the observer and the sun, and this is the angle. This angle is going to be positive from here to the vertical, and this angle would be the zenith angle. The sum of the elevation angle and the zenith angle is going to be 90 degrees. Now we must define other angle, and it is clockwise angle. Clockwise angle is the angular distance of the sun to the east-west with respect to the local meridian. In our case, the local meridian is the north-south line. We are here, the observer, and here is the sun. This is the vector of between the observer and the sun. This is the local meridian, and this is the sun's path. So the clockwise angle is the angular distance from here, the local meridian, to this position, and it's going to be lower than 0. If it is measured from the east, it's going to be 0 if the sun is here in the local meridian, and it's going to be higher than 0 if it is in this point. Solar azimuth angle, which is the angular distance formed by the south and the projection of the trajectory of solar radiation, and really is more or less the same that clockwise angle, but the difference is that clockwise angle is measured in the sky with the help of the sun's path, and here it is measured in the horizontal plane. Incidence angle, which probably is the most important angle, because it's going to be the angular distance between the normal vector of the surface of our parabolic trough and the vector of the solar ray, and it's going to be 0 if both vector match, and it's going to be 90 degrees, for example, if the sun, when the sun rises and when the sun sets, because the sun is here and our normal vector is here, so the angle is 90 degrees. Here we can see this concept, that is, normal vector of the surface is this, and the vector associated with the solar ray is this. So the incidence angle is going to be 0 if both match. And finally, the solar tracking system is based on two main angles. It is solar elevation or solar height and solar azimuth angle, which are going to be very useful to determine the components of the solar vector, that is in the x direction, y direction, and z direction. To finish this unit, we must define the different concept of the sun. In both hemispheres, that is in northern hemisphere and in southern hemisphere, the sun rises in the east and it sets in the west. The maximum irradiance is going to be in a given period called noon, and this is in northern hemisphere at 12 o'clock, more or less, because the incidence angle is close to 0. However, it is much more interesting to know the solar position throughout the day instead of knowing the sun position throughout the day. That is, we must define the movement of the sun throughout the year. Here in early morning the sun is rising in the horizon, so the angle is 90 degrees, the incidence angle is 90 degrees, although here we are measuring the angle respect of the observer, and it is 0 angle. In mid-morning the sun is getting higher, that is, the incidence angle is decreasing, and in noon the sun is at the zenith and this is directly overheat and the incidence angle is 0 because both vector match. And here we have the opposite process, because at the afternoon the incidence angle is getting higher, and here is the same, it is 90 degrees, because here is the normal vector of our surface, of our parabolic trough, and here is the solar ray, so then the incidence angle is 90 degrees. Here we can see an example of this concept, and this is the sun rises in the east, and in a given period from more or less 11 o'clock to 1 o'clock, that is the noon period, the incidence angle is more or less 0. Although the Earth is rotating around the sun for our purposes, it must be understood that the sun has a movement throughout the year. So we can see, for example, that the movement throughout the year is the same. In summer the sun hours are higher than in winter. Here we can see the yellow circle, which is higher than in winter. For example, in the northern hemisphere we have got sun hours from 6 a.m. more or less to 10 p.m. and on the other hand we have that in winter the sun hours start at more or less 8 o'clock, 8 a.m. and they finish at more or less 6 p.m. so the difference is very high. And on the other hand we have the equinox. Today, for example, is 21st of March, and the number of hours of day and night are more or less the same, and also in 21st, 22nd of September, which are the number of hours of day and night are more or less the same. Here we can see the same concept, that in northern hemisphere the incidence angle is higher here in June, so the irradiance is going to be higher, and here the number of hours of sun is higher in summer than in winter. we can see that this semicircle is much more higher than in December. To finish this unit, we must understand two concepts, and this is an lemma and equation of time. We have that the plane of the Earth is not a circle around the sun, but it is an ellipse, that is an elliptical orbit. And we have got that the Earth axis has an angle respect of this plane, and it is 23.5. So the lemma and the equation of time is going to be the result of the sum of these effects. The equation of time is the difference in minutes between the average solar time, that is the hour measured by our mobile phone, for example, and the apparent solar time measured by a sundial, that is a solar clock. For example, in November, we have that the average solar time is more than 16 minutes behind apparent solar time. That is, if our mobile phone is 8 o'clock, for example, the apparent solar time, that is the sun position, is going to be 8:15 minutes. And on the other hand, we have mid-February, that it is the opposite. The average solar time is going to be 14 minutes ahead of apparent solar time. Here we can see that the black plot is going to be the sum of both effects. Some shift due Earth tilt and some shift due to elliptical orbit. And finally we have the lemma concept. An lemma concept really shows the equation of time, but in a plot. In the y-axis on the chart represent the declination of the sun in the sky for 1 year, going from minus 23.5 degrees to plus 23.5 degrees. So the total movement of this axis is 47 degrees. And as we saw in the previous picture, in early November, the apparent solar time has 16 minutes more than average solar time. So if our clock has 19:45 minutes, the real sun hour is 8 o'clock. So the night is reached in a shorter time. And on the other hand, we have that in February the average solar time goes more than 14 minutes ahead. So if our clock has 19:45 minutes, the sun hour is 19:31. So the night is reached in a bigger time. Here we can see this concept in February and in November, that the difference is higher. And here this concept is plotted in the sky. So finally we have finished this unit.